Hi, my name is Nicholas, and for my Raspberry Pi project, I built a full video surveillance system using a Raspberry Pi 4B, a USB webcam, Docker, Motion Eye, and cloud backup. The idea was to make something that actually works in real life instead of just a demo. In this presentation, I'm going to walk through why I chose this project, how it connects to a bunch of Raspberry Pi architecture topics from this class, the exact steps I followed, a demonstration of the system working, the troubleshooting I had to go through, and finally a few things I'd do differently next time. I wanted to solve a real problem. Home security cameras are either expensive, require subscriptions, or lock you in their app. I have one of those. But a Raspberry Pi gives me full control for way cheaper. I can pick the camera, decide where the files get stored, Dropbox, Google Drive, and actually understand how the data flows instead of just trusting a black box. I also wanted something I could repurpose for later. I could turn this into a pet cam, a dorm room monitor, or a general purpose recording system. The Pi is perfect because it's low power, silent, and flexible. Plus, this kind of project forces you to connect multiple concepts: the hardware, Linux, networking, video encoding, cloud syncing. Everything we've talked about in class shows up somewhere. So, here's the big picture. A USB camera connects to the Pi runs Motion Eye inside a Docker container, and Motion Eye handles everything from motion detection to saving video clips. When the Pi detects motion, it saves a file locally. Then, I use rclone to automatically sync that file to Google Drive. I can open a web browser on my laptop or phone and see a live feed, change settings, or check recent recordings. What I liked about this setup is that it's modular. The hardware, the OS, the container, the application, and the cloud storage all do separate jobs, but they fit together. That helped me understand the Pi as more than just a mini computer. It's a whole architecture designed to connect components like this. One of the biggest architecture connections is the CPU and instruction set. The Raspberry Pi 4B uses the ARM Cortex-A72 processor. ARM instructions are designed for efficiency, and that matters a lot here because the video processing is intensive. When Motion Eye encodes video, it uses H.264 encoding, which is supported by the Pi's hardware through V4L2. If I chose the wrong encoder, like NVENC, the CPU would basically panic because the encoder only works on NVIDIA GPUs. Using the correct hardware accelerated encoder made the system smoother and lowered the CPU usage. This helped me to connect our class discussions about instruction sets, hardware acceleration, and processing performance. Before doing this project, I didn't think too much about how a camera stream can actually become an encoded video file, but now I understand exactly where the CPU comes in. Next is the memory and storage. Video recording isn't light, and each frame has to be stored in memory before encoding, and the Pi doesn't have a ton of RAM compared to a normal computer. If the encoding's too slow, frames pile up and get dropped. I also had to think carefully about storage. The SD card I have isn't meant for consistent heavy writes, and the video files grow fast. So Motion Eye organizes everything into folders based on the date, and then rclone uploads the files to Google Drive to keep the SD card from filling up. That made the system more reliable in the long term. This part helped me understand why storage architecture matters so much. Even small decisions like clip length or video format, resolution, completely change how memory and storage the Pi needs. The I/O system ended up being one of the most educational parts. My USB camera shows up as Dev Video 0 and Dev Video 1, and those paths are created by the Linux kernel using UVC drivers. Sometimes these device numbers change when I unplugged the camera, which broke my Motion Eye until I fixed it. But inside Docker, I learned that I had to explicitly pass the camera devices into the container. Otherwise, even though the Pi saw the camera, the container had no idea it existed and had no access to it. That made the connection between kernel-managed devices, user space applications, and containers really clear. This ties directly back to class topics on input and output control, how peripheral communicate through the South Bridge, and how the OS abstracts hardware for software. Networking popped up in a few places. First, MotionEye runs a web server on port 8765, so I can view the live stream anywhere on my local network. The Pi also has to upload files through HTTPS to a Google Drive using ArcLoan. That means it consistently talks to both the local network and the internet. I had to think about bandwidth when streaming high resolution video and also about latency when syncing the files. If the Pi was uploading a large clip, the web interface would slow down a bit. That made networking topics like protocols, ports, and throughput feel very real. The operating system ties everything together. Raspberry Pi OS manages USB drivers, networking, and the file system. Docker runs MotionEye inside of a container, which isolates it from the rest of the system and makes it much more stable. I use Docker restart policy so that if the Pi ever reboots, if I turn it off and I plug it in somewhere else, the container would automatically start up again. That taught me how to process control and service management work in Linux. Before this project, I never thought about how many layers were involved just to run one application. Now I have a much better picture on how the OS, kernel, and applications all interact. So here are the procedures in more detail because this part really shows how everything came together. After updating everything, the first thing I did was enable SSH because I didn't want to plug in a keyboard and monitor every time I made a change. But in the video I'll show later, I had it hooked up without an SSH connection. Working remotely really just made the whole process smoother. Next, I installed Docker. This wasn't really required, but I chose Docker because it keeps MotionEye isolated and makes resetting and restarting way easier. If anything broke, I could just recreate the container instead of reinstalling the whole application. And setting up only took a couple of commands, and once Docker was installed, I created 2 folders in my home directory, one for MotionEye's configuration files, and one for all the recorded videos and pictures. Then came the actual Docker run command. This was one of the trickier steps because MotionEye needs direct access to the camera. That meant I had to pass the DevVideo0 and DevVideo1 devices into the container. If I forgot those, MotionEye would start normally but act like no camera existed. So the run command included all the port mappings, volume mounts, and device mappings. Once the container was running, I opened a browser and went to the Pi's IP address on port 8765 to access the MotionEye interface. That's where I added the camera. At first, it didn't show up correctly because the video format was incompatible, but after fixing that, I was able to choose the right resolution, frame rate, and encoding format. I played around with some of the settings to find the best balance between video quality and performance. Then, I moved on to setting up the cloud synchronization. I used ArcLoan for this. It walks you through linking your Google Drive account and generating a token. Once it was connected, I created a sync command that mirrors the Pi's media folder to a Drive folder. I tested this a few times by recording short clips and watching them appear in Drive 10 minutes later, because that's what I had set the sync time from my folder to my Google Drive. After that, I tested motion detection by walking in front of the camera. I watched how MotionEye created these folders, named the files, and adjusted the motion sensitivity until it felt right. Finally, I made sure everything worked on reboot. I restarted the Pi and checked whether the Docker container started automatically and whether the camera feed came back online. After a couple small adjustments, everything worked exactly how I wanted. In terms of results, the system ended up being more solid than I expected. The live feed from the USB camera works reliable in the MotionEye interface. It loads fast and looks clean, and I can adjust things in real time like resolution and frame rate. When the camera detects movement, MotionEye automatically creates a video clip with a timestamp. The naming system makes it look easy to know exactly when something happened. The video files are organized by date in the media folder, which keeps things tidy. One of the biggest results is that the cloud upload actually works in the background. After 10 minutes, ArcLoan picks up the folders and syncs it to the Google Drive. When I check my Drive folder, the clip was already there, even if I shut down the Pi. This gives the project a reliable backup system. Another result I didn't expect was how stable everything became once Docker was configured correctly. I could restart the Pi, unplug it, change Wi-Fi networks, move somewhere else, and the service came back automatically every time. It really made the project feel like a real, deployable device instead of a school assignment. Overall, the system behaves just like a small home security camera setup. It streams, records, organizes, and uploads footage without me needing to touch it. I definitely want to go deeper into the troubleshooting because this is where most of the actual learning happened. One of the earliest problems was that the camera randomly switched device numbers. Sometimes it would show up as dev video 0 and other times it would show up as dev video 1. This completely broke MotionEye because the container was only mapped to one of them. I used V4L2 CLT list devices to figure out exactly which device belonged to the camera, and once I understood how Linux assigns video devices, it made sense. Another headache was MotionEye showing up a gray screen. For the longest time, I thought something was wrong with the camera or the USB cable, but eventually I realized I'd chosen an NVIDIA coder for the movie format. So NVENC, which obviously doesn't exist on a Raspberry Pi, doesn't work. So it didn't throw an error at first, it just silently failed. So switching to H.264 V4L2 M2M encoder fixed the gray screen immediately. I also ran into an issue where only pictures were being saved but not videos. That one was confusing because the camera feed looked fine, but after digging into the logs, I found that the root directory in my MotionEye settings were wrong. It pointed to a folder that didn't exist, and once I corrected it, the video started saving again. Another small but time-consuming issue was file permissions. I tried to delete some old JPEGs and folders and test stuff from the media folder, but it denied me, so I had to change the ownership of the whole folder so that my user account could manage the files. And even the cloud upload setup had some bumps. The first time I tried reconnecting ArcClone to Dropbox, it rejected the request, so I switched to Google Drive. And I also had to test the sync multiple times to make sure it wasn't overwriting files or missing anything. But each problem pushed me to understand a different layer of the system, whether it was Linux, Docker, the camera drivers, or MotionEye application. Looking back, those issues were frustrating, but they really taught me the most. I also learned a ton from this project. I got comfortable with Linux commands, Docker, device mapping, video encoding, and networking. I also learned that debugging is a huge part of real IT work, and almost nothing works perfectly the first time. And that was kind of the point. The mistakes are what forced me to understand the architecture on a deeper level. If I did this again, I'd probably try adding multiple cameras or even running detection with the machine learning model. We'll see. And thank you.